well as identification of design constraints. And then we can conduct material management. From this, actually allows us to calculate the string information, such as flow composition, as well as temperature value. And subsequently, we can actually perform equipment initial design calculation. This allows us to get some general idea about the equipment specs. Finally, we'll be conducting a parametric analysis on some of the important design parameters. Hopefully, we can optimize the plant performance. I particularly would like to talk about the design strategy I used in stage 2 and 4. About the establishment of design basis. This is basically an iterative process. Can be broken down into 5 different steps. The first step is to assume an initial design basis, serve as a starting point. These values were recommended by the census engineer. A water rate of 1,000 barrels per day, air rate of 50,000 centicubic feet per day. Next step is to looking for design constraints. The 2 major constraints we identified in this project. First is the power limitation. The ASP building can only supply up to 50 kilowatts of power, and most of this power goes to the 2 energy intensive units, which is the compressors as well as pumps. The other important constraint we identified is the land requirement, because the well site is located in very confined space. This particularly applies to the separator design as well as the tank design. Yeah. And so we play around with different flow rates, and by doing so, we can actually generate the different power and consumption values as well as dimensions of the equipment. And we try to make sure that all the values actually fit into the 2 limitations we identified. In the end, these are the final operating conditions we identified. They are the maximum and minimum rates of water and the air flow rates. Next, I would like to talk about the separator design, which is an important component of stage 4. Separator design can be broken up into 5 stages. First stage, we actually calculate the settling velocity. Subsequently, we can actually estimate the cross-sectional area of the separators. And then by selecting appropriate retention time, as well as comparison between the gas and liquid gas capacity, we can actually calculate the overall volume of the separators. Finally, we check for the standardized ratio to confirm the final dimension of the separators. This process is also an iterative process. The next important design is the compressor design. This figure here actually illustrates how we come to about the compressor spec. The first important parameter we need to know is the in-lab conditions. From this onwards, we can actually calculate the adiabatic efficiencies, compression ratios, as well as volumetric efficiency. And then finally, use these 3 important information, we can calculate the compressor power consumption, as well as the discharge temperature, and also the compressor speed. Now let's jump to the final segment, which is the project results and the analysis. The first important result came out from this project is the process flow diagram. This is a direct result of material and energy balance. And the diagram here is pretty much self-explains itself. The important thing to notice here is that the orange line represents the gas flow or the air flow. The blue line here represents the water flow, and the red line in the middle actually represents the 2-phase flow. Also, I'm not going to go into detail on the downhole completion side, which Adam already explained all this. Just quickly notice that there are a few control loops. First of all, we have pressure control is the separator outlet, which allows us to adjust the air outlet rate. We also have a level control to connect to the separators, is the separator outlet. Finally, we have a control valve, is the air compressor outlet, which allows us to adjust the air rate going into the well. The next important result came out of this project is equipment specification. The first equipment that was selected was the 2-phase horizontal separator. An important fact to notice here is, first of all, is the retention time. Typically, for a two-phase separator, the retention time is anything between 30 seconds up to 3 minutes. And the reason why we choose 4 minutes is because I think we're dealing with water and air here, and we're not too sure, and this was strongly recommended by the sensor engineers. The other thing to notice is the pressure rating values here. And the pressure rating is very extremely important. If this pressure rating is too small, we cannot actually providing enough force to push the water from the separator to the tank. If this pressure value is too high, then we actually affect the drawdown of the overall well, and we subsequently reduce our production rate. The next equipment I would like to talk about is the compressors. We actually selected the screw-type air compressors in this case, and notice that we have a very high maximum discharge pressure. This high discharge pressure actually affects the compression ratio as well as discharge temperature. I'm going to talk a little bit more on this in the parametric analysis section. Also note the efficiency values. Typically for a compressor or a pump, the efficiency value ranges anything between 50 to 70%, according to Carlson, Richardson, and Chemical Engineering Handbooks. In this case, I'm just putting the average value here. The next equipment is the centrifugal pump. An important facts to notice here are the last three information: the MPSHR, MPSHA. MPSH stands for net positive suction head. A here stands for available. R here stands for required. MPSHA must be greater than MPSHR at all times in order to prevent the cavitation from happening. The final result came out from this equipment specification is the pipeline design. Notice that we use carbon steel as the pipe material. This is mainly due to that the simple characteristics of the process fluid we're dealing with. Also, the pipe diameter here. This is primarily estimated from a correlation proposed in Carlson Richardson Chemical Engineering Handbook. We also produced the plan layout. We can see that the space is actually quite small. We actually managed to fit in a lot of equipment in such a confined space. Also note that the code DM50, DM80, and DM102, these are the pretty standard codes, pipe diameter codes used by vendors. 50, 80, and 102 represent 2-inch, 3-inch, and 4-inch respectively. Okay, finally we jump into the parametric analysis. The first thing I decided to do is to plot the compressor discharge pressure. This is the water rate. The reason why I'm doing this is because in order to pump your air to the bottom hole, you need the pump discharge pressure must exceed the well pressure. The well pressure is made up of the separator back pressure plus the pressure loss in the pipeline plus the fluid coil pressure, and that's why I decided to plot discharge pressure with water rate. The overall trend of this graph shows there is an increasing trend as the water rate increases. But if we look more carefully, we actually can see that it's a lower water rate region. The change of the slope is actually quite steep compared to the higher water rate region. This can be explained by the following equation. The important assumption made here is that we're only dealing with bubble flow regime, and also due to the time constraints, we actually did not take water hold up into consideration. So we can see that it is lower water rate by looking at the last equation here, that any increment in the water rate would actually have a larger effect on the numerator of the final equation than the denominator. This would actually result in a higher weight fraction of the water phase, and ultimately impact on the discharge pressures. If we go to the higher water rate regimes, we can actually see that the effect on the final equation is reversed, and this time we actually have more effect on the denominator rather than the numerator, and this leads to a plateau shape in terms of